Imagine a road that does not just carry cars, but quietly turns sunlight into electricity beneath their wheels. It sounds like a perfect idea for the energy transition, and that is exactly why the world fell in love with it. But when engineers tried to build this dream in the real world, the road began to fight back. Because a highway is one of the harshest environments you could ever choose for a solar panel. And that contradiction created one of the most fascinating cleantech experiments of the modern age. The question is no longer whether solar roads look futuristic, but whether they make any sense at all. To answer set, we have to follow the technology from bold promise to brutal reality. And what we find is not just a story about roads, but about how innovation collides with physics, money, and scale. The dream behind solar roads was simple and irresistible. Roads already cover enormous amounts of land, so why not turn the dead surface into a power plant? In theory, every parking lot, bike lane, sidewalk, and service road could become part of the energy system. That promise was especially attractive in countries trying to decarbonize without sacrificing more land for solar farms. Instead of choosing between mobility and energy, solar roads seemed to offer both at once. It was the kind of idea that looked obvious the moment someone said it out loud. And like many ideas that feel obvious, it turned out to be much harder than it first appeared. The first wave of excitement came from experimental projects in Europe and the United States. In the Netherlands, the solar road bike path became one of the earliest serious tests of the concept. It was not a highway, and that detail mattered more than most people realized. Lower speeds, lighter loads, and more controlled use made bike paths a far safer laboratory for the technology. Then France raised the stakes with one of the most famous pilots ever built, the Wattway Road in Normandy. This was not a small sidewalk experiment, but a public road designed to prove that solar pavement could survive real traffic. For a moment, it looked like the future had arrived in plain sight. But the future was about to meet rain, trucks, dirt, and time. A solar road is basically a photovoltaic system forced to pretend it is pavement. Under the surface, there are solar cells similar in purpose to rooftop panels. Above them, engineers add a protective layer that must be transparent enough for light and strong enough for traffic. That single requirement creates the central engineering paradox of the entire technology. The rougher you make the surface for grip and safety, the more you scatter the sunlight before it reaches the cells. The smoother you make it for better solar performance, the more dangerous it becomes for vehicles and pedestrians. Then come heat expansion, water infiltration, dirt buildup, impacts, and the brutal weight of repeated traffic. A normal solar panel wants to sit still, tilted toward the sun, cool, clean, and untouched. A road offers almost none of those conditions. Once real pilots began operating, the performance gap became impossible to ignore. The famous French Wattway test in Turova drew attention because it cost millions, yet produced far less electricity than expected. In its first year, the site generated roughly half of the energy target that had been publicly discussed. Output then dropped further as wear, damage, and operating limits took their toll. Reports later described the project as dramatically less effective than conventional solar panels installed in easier conditions. And that exposed the most uncomfortable truth of all. The road was asking solar technology to do its job in exactly the wrong place. Even supporters began shifting away from the fantasy of powering cities with highways. Solar panels perform best when they face the sun at the right angle, and roads are almost always flat. Roads are also frequently shaded by vehicles, buildings, trees, signs, and even the dust kicked up by traffic. They get hotter than rooftop arrays too, and higher temperature usually means lower photovoltaic efficiency. Then there is maintenance, because every tire mark, leaf, oil stain, and patch of dirt steals a little more light. Cleaning a solar farm is easy compared with cleaning an active road without disrupting transport. And when a conventional panel fails, you replace a panel. But when a solar road section fails, you are also dealing with public infrastructure. That means cost, traffic management, safety, liability, and downtime all hit the equation at once. Suddenly, the elegant concept starts looking like a maintenance nightmare with a power cable attached. But here is the twist that keeps solar roads alive. The concept did not completely fail, it simply shrank into more realistic use cases. Instead of trying to power neighborhoods, newer systems often target small nearby equipment that is expensive to connect to the grid. That includes warning signs, streetlights, surveillance cameras, bike charging points, and smart roadside devices. In that role, the road is no longer competing with the best solar farms on Earth. It is competing with the cost of trenching cables, digging sidewalks, and extending electrical infrastructure to awkward places. And in those narrow cases, the economics can start to look much less absurd. That is why companies like Colas moved toward products such as Wattwaypack for localized roadside autonomy. The dream became smaller, but also smarter. Solar roads matter because they reveal a pattern seen again and again in breakthrough technology. A concept can be visionary, technically possible, and still be wrong for large-scale deployment. Physics does not care how elegant the pitch deck looks. Materials wear down, sunlight arrives at bad angles, budgets run out, and maintenance crews inherit the consequences. Yet, experiments like this are still valuable because failed ambition often teaches more than safe incrementalism. Without bold pilots, nobody would know where the real boundary lies between possible and practical. And solar roads drew that boundary in bright, expensive detail. They showed that covering roads with solar panels is not impossible, just usually inefficient compared with better options. That distinction may sound disappointing, but it is exactly how mature engineering is supposed to think. So, what is the future of solar roads now? Most likely, they will survive not as a revolution under every highway, but as a niche tool in difficult locations. Expect them where land is constrained, grid access is awkward, visibility matters, or demonstration value is part of the goal. New materials may improve durability, and smarter electronics may squeeze more value from every watt. But no breakthrough coating can change the fact that roads remain terrible solar environments compared with roofs and open fields. The winning strategy may be to stop asking roads to be power plants first and start asking where they can be useful energy surfaces second. That subtle shift changes everything. It turns a failed moonshot into a specialized piece of infrastructure logic. And in engineering, that kind of reframing is often how real progress begins. In the beginning, solar roads promised a world where every mile of pavement could help power civilization. In the real world, they delivered something smaller, stranger, and arguably more honest. They reminded us that innovation is not just about dreaming bigger, but about discovering where a dream actually fits. Because the most dangerous words in technology are not "this cannot work," but "this sounds too good to question." Solar roads did work, just not in the way the headlines wanted. And that may be the real story worth remembering. Not every futuristic idea becomes a global revolution. Some become something quieter, narrower, and more useful than anyone expected. So the next time you hear about a road that generates electricity, the real question is not whether it is possible, but whether it is the right road, in the right place, for the right reason.